The medullary concentration gradient is a crucial physiologic process that allows the kidney to concentrate urine. In humans, the inner medullary interstitium has a concentration of 1200 milliosms per liter. If the inner medulla is adequately concentrated, when indicated, the kidney can reabsorb water, thereby concentrating the urine to as high as 1200 milliosms per liter. To achieve this, the following needs to be in place. 1. Countercurrent multiplication process involving the loop of Henle. 2. Capillary networks surrounding the loop of Henle known as the vasa recta. 3. Urea recycling. And 4. Presence of antidiuretic hormone, ADH, also called arginine vasopressin. Urine concentration is a necessary process in maintaining homeostasis, including isoosmolar states and defending low-volume states. Countercurrent multiplication occurs in the loop of Henle with juxtamedullary nephrons. Juxtamedullary means the glomerulus remains in the cortex, but near the corticomedullary junction, with the loop of Henle extending all the way into the inner medulla. The term countercurrent refers to the fact that the descending and ascending limbs of the loop of Henle flow in opposite directions, enabling the exchange of water and solutes in a fashion that concentrates the medullary space. This process requires that isotonic filtrate, around 300 milliosms per liter, is delivered to the loop of Henle from the proximal convoluted tubule, and is ultimately used to concentrate the inner medullary interstitium to 1200 milliosms per liter. So how does the kidney do this? In part, it uses countercurrent multiplication. Multiplication reflects how a small active transport process is amplified to create a large osmotic gradient. In the kidney, it is a coordinated combination of three important processes. 1. A secondary active sodium transport from the thick ascending lumen into the interstitium. 2. The countercurrent associated with the loop of Henle. And 3. Specific loop section membrane permeabilities. To understand this, let's go into more detail. First, remember that the thin descending limb is permeable to water and impermeable to most solutes. The thick ascending limb is permeable to solute and impermeable to water. Solute moves out of the thick ascending limb through the sodium-potassium 2-chloride channel. This secondary active sodium transport is enabled by the basolateral sodium-potassium ATPase driving the reabsorption gradient. This increases the concentration of the interstitial space, creating a concentration gradient, enabling water molecules from the thin descending limb to diffuse across the membrane. This in turn concentrates the filtrate in the descending limb. As a more concentrated filtrate is delivered to the distal section of the loop, which includes the thick ascending limb, the NKCC2 will continue to allow solute down its concentration gradient into the interstitium. Again, water from the thin descending limb diffuses across into the interstitium to concentrate the filtrate, which again in turn supplies the thick ascending limb with a gradient enabling solute transport back into the interstitium. This process continues until the interstitium reaches a concentration of approximately 600 milliosms per liter. We can only reach around 600 milliosms per liter with this process since there are only a few thick ascending loops that extend far enough into the inner medulla to form the maximum 1200 milliosm per liter interstitial concentration. To get to 1200 milliosms per liter, there's another mechanism at play called urea recycling, which we will discuss in just a moment. Before we get to that, though, I'd like to depict more simply how this process concentrates the urine and medullary interstitium. The vasa recta, which is the peritubular capillary supplying the blood to the loop of Henle, represented by this red loop, helps maintain this medullary gradient, preventing washout. The vasa recta is situated where it flows in the opposite direction of the loop of Henle, creating another countercurrent, if you will. In this case, it is termed a countercurrent exchange. Blood with a lower concentration, approximately 300 milliosms per liter, enters the outer medulla, running countercurrent to the loop of Henle. Concentrated filtrate from the ascending thick loop of Henle enables the gradient for a solute to be pumped from the loop into the interstitium. Because the osmolality of the vasa recta at this level is also comparatively low, solute diffuses into the vasa recta as well, concentrating it. The blood becomes increasingly concentrated as it moves into the inner medulla, reaching 1200 milliosms per liter. As the vasa recta blood flow returns towards the outer medulla, water diffused from the descending loop of Henle follows the concentration gradient into the more concentrated vasa recta. During its ascension, the blood within the vasa recta becomes increasingly dilute. Again, this maintains the gradient, preventing medullary washout. But our job is not done yet. Urea recycling is responsible for the remainder of the medullary concentration gradient, ensuring the inner medulla reaches an impressive concentration of 1200 milliosms per liter. Again, this is an important process that enables the kidney to concentrate the urine in periods of high serum osmolality or states of low effective arterial blood volume. We discuss this mechanism in the sodium and water chapter further. Selective sections of tubular urea permeability are necessary for this mechanism to work. The nephron is largely impermeable to urea, except in a few locations, which are 1. The proximal convoluted tubule, whereby urea is generally reabsorbed with water down its gradient. 2. The thick descending loop of Henle, whereby urea is secreted from higher medullary concentrations back into the tubule via diffusion. And finally, 3. In the medullary collecting duct, whereby reabsorption is mediated by ADH. Let's look at this more in detail. The urea concentration of the blood is 5 milliosms per liter. Urea is freely filtered by the glomerulus. In the proximal convoluted tubule, urea, which is a water-soluble molecule, is reabsorbed with water, which means the urea filtrate concentration delivered to the loop of Henle is still low compared to the medullary space. In the descending loop, water diffuses into the medullary space, as we discussed earlier in this tutorial, concentrating the urea downstream. In the presence of ADH, water is also reabsorbed along the distal convoluted tubule and cortical collecting duct, both of which are impermeable to urea. This further concentrates urea distally. As urea reaches the medullary collecting duct, ADH-sensitive urea channels exist that reabsorb urea down its concentration gradient from the filtrate. As we will learn in later modules, ADH also facilitates water reabsorption via aquaporins, the final process of urine concentration. Finally, at the descending loop, urea-specific channels allow urea secretion down its concentration back into the tubule. This process repeats itself, resulting in a highly concentrated inner medulla, which is our urea recycling process.